Great. Thank you so much for coming back. I know that fourth floor balcony with the sun shining is a great place to start in San Francisco on a Saturday. So we're really happy to have you here. My name is Zeenat Patrawala, and to briefly introduce myself, I am a part of Google Medical Brain, which is the deep learning team at Google, and we're focusing on a lot of our work in healthcare applications. I am on the business side, so hopefully we'll be able to give you a perspective or questions that fulfill everyone's needs here. But just as a quick poll, how many people here are entrepreneurs or startup folks? Investors? Individuals with deep machine learning and engineering experience? And business folks or other people who are just interested in the space? All right, perfect. Well, great. So our format for the next 80 minutes here is I have some of the world experts in the space here on stage with me. So we'll be doing 20 minutes with each of these individuals as a fireside chat. We're going to be kind of talking through for about 15 minutes and then opening up for Q&A for about 5 and hopefully getting 1 or 2 of the audience questions. So without further ado, let me introduce our first guest. Hi, Jim.
Hi.
Thank you so much for joining us.
Thank you for having me.
I think we could spend our entire 15 minutes discussing your incredible career, but just to sort of briefly introduce yourself, you are a professor of neuroscience and the head of the Department of Brain and Cognitive Science at MIT. You have a background as an MD, PhD, and have focused your entire career in research. Is that?
That's correct.
Okay.
Everything perfect.
Okay, great. Well, to get us started, I wanted to sort of start with the work that you specifically do in your lab around neural circuits and sensory cortical processing. So maybe as an introduction to the space, if you can tell us a little bit about the work that your lab has done in terms of research on brain and human and primate brains.
Right, okay, yes, again, thank you for having me. So my lab, when I started my lab at MIT in 2002, I was really fascinated by the problem of how you can recognize faces and objects and how human brains do that quite effortlessly, but machines at the time were very, very bad at that. And we knew the brain regions that were involved in this. And we said we could probably study this and start to get some understanding of how the brain does this much better than machines. So that seemed like a great research front at the time. We really didn't know how it worked, but of course understanding how objects are identified in this world are critical to higher cognition. It's sort of an entry point to cognition, even though you could just say that's just vision. It's just the beginnings of broader intelligence. My lab focused on how non-human primate brains work and how the neural activity flows through the visual stream, a part of your brain called the ventral visual stream, where you capture an image on your eyes and then the data are transformed to some other pattern of neural activity that allows you to say, I see a face, or I see a car, or I see a dog. So again, we didn't discover that part of the brain. It had been known before that that's where the action was. We just didn't really have a working model of how it happened. So the big picture here is a lot of work had gone on to say these parts of the brain are important to this kind of entry cognitive process, but engineers hadn't yet come up with a model of how that might work. So again, computers were bad at the time at that. And similarly in parallel in computer vision, what was going on is people were building sort of hand-built models of certain features. You should detect edges in the scene, and then maybe you're going to put those together in some right way. And what really sort of, now just fast forward over about 10 years, what really happened, we're busy collecting data, measuring things. We didn't understand how it worked yet just by measuring data. But what happened around, in beginning in my lab around 2008, we started to just play with deep networks that were approximating the brain. So many of you may not know the brain is sort of one of the inspirations for deep networks because you have this multi-layered processing system that processes things locally. That's called the convolutional deep neural network. And so but what was amazing is that our computers got better, tricks for training deep neural networks got better, ways of searching the spaces of different deep neural networks got better. And it was, I guess, fortuitous that we were able to show that some of those deep neural networks, when you train them to be good at computer vision tasks like recognition, that led to gains in computer vision, but they also, and this is what my lab most showed, that the internals of those networks started to look more and more like the internals that we were measuring in the brain. So there was sort of a convergent evolution between efforts in training deep neural networks for visual tasks and what was actually going on in the brain, which is, again, what my lab was measuring. And so a lot of our work has been showing the convergence of those two. And this is kind of a cross-pollination, if you will. You have science sort of informing that, hey, you should build vision systems that look like this, where you also have engineered systems that are now hypotheses, the best hypotheses of how our brains might work, at least for this early cognitive process. So that was sort of a summary of about 15 years of work.
Okay, well, perfect. So just so from my understanding, so it sounds like the framework of the biological system is actually what was applied to the engineering world in developing these deep neural networks.
Right.
So from that time,
well, I would just say it's never quite that simple, right? It's not as if brain scientists read out the blueprints and hand it to engineers and then they build it and it works, right? It's an interplay between ideas and constraints along the way, some of which turned out to be relevant, others of which turned out not to be so important to constraining the development of systems. I think that's just an important meta point as these two fields work together. It's not as if brain scientists have all the answers as to here's how to build an intelligent system. In fact, again, that's what's exciting for us is a synergy between systems that are trying to be intelligent and this actual intelligent systems, 3 pound, 20 watts behind each of our eyes that we study every day. And so that's quite exciting. And this is an example how science and engineering work together. It's not as if one leads the other. They work together to get to answers that help both of them.
Okay. Well, in that vein, then, what were some of the unique findings in terms of the learnings you gained from the science perspective that really informed the engineering, or learnings that you gained that you were surprised didn't inform the engineering process?
Well, I mentioned a few of them. So the fact that you should work with a deep network more than 2 layers, approximately 5 layers at the time, that you should process the image locally, which is the convolutional part of deep neural networks. But then there were assumptions that now they're still debated in our field. So for instance, the current models don't track, you may know that neurons communicate with each other through spikes. They send little action potentials to talk to each other. The field still debates whether those are important to the actual computational function. But we didn't need to include those to actually get the networks to look a lot like the brain. So this, again, it sort of said that may have been a distraction to be too focused on spikes at the time. That doesn't mean spikes aren't important to the brain. It's just that turned out to not be critical to the progress that we've seen recently. So that's an example of something that, again, shouldn't be dismissed, but wasn't critical to that particular progress. And there are many other examples. The brain is full of myriad details, of course, right? And we don't know which ones that we should pay attention to. And that depends a lot on what your goals for doing, what you're actually trying to do with that knowledge.
And well, then, in terms of where we are in 2018, does your research find that we are still in a progress of converging these two disciplines, or are we now going in two separate directions? Right,
that's a great question. So we actually think about this a lot in the lab, right? So companies like Google and others are busy trying to engineer even better and better networks. So part of sometimes we'll sit around in the lab and say, we can just wait for engineers to build something, and some of these will turn out to be like human cognition, and we'll just later figure out which ones are most like the brain. So I think that's a little bit too optimistic because they're not engineering under the constraints of the brain. They're engineering under various goals of whatever their business model might be at the time. So we in our case, the micro case of vision that, again, to my lab, we monitor networks. So networks, you may know, started off at sort of first deep network was AlexNet in 2012, was about 8 layers deep. The current networks are now about 170 layers deep. So they took that deep idea and put it on steroids, right? And they're still improving in their performance, but we monitor them. Those networks are looking less and less like the actual visual system. So that's an example of the divergence between where technology is driving and what the brain is actually doing. They still offer clues to how the brain might be working, but that gets a little bit into the weeds that I maybe don't want to to drag us into. So we can't just wait for them to occur. We have to build them ourselves and that's the goal of a brain scientist, really, is to come up with actual working models of the brain, to do science like engineers.
Well, I think the last question I'm going to ask on this topic then is what is, in your mind, the key success from the visual intelligence research? What can we learn from that? And I know that you also think about the brain and cognitive sciences from a much broader perspective as the department head. So how is that translated to additional work in your...
Right. So I think I touched on it, but I'll say it again. The key progress was really the idea that you can't just make measurements of the brain and behavior. That's what's called a natural science. You can't just engineer and hope that you might get something that looks like the brain. Computer vision didn't succeed by just engineers thinking about what to do. So the actual combination of those two, science plus engineering, led to these advances, which were deep networks for vision, which now is just called deep learning because you can apply a lot of those common techniques to any aspects of data processing, as the technology folks in the room realize well. And I should also point out that the learning rules for those models were actually, they were first published in cognitive science journals by people trying to study human learning. So there's a long history of interacting science and engineering. So the main lesson I take is we have to converge science and engineering if we want to make real progress on intelligence, and that's just one example. And again, this is vision that you do in just a glimpse. The first 200 milliseconds, you can recognize objects quite well. That's what my lab studies. But understanding a scene or larger intelligence, those are much harder problems that we don't yet know, and that leads into sort of where we're headed next. So at MIT, we have various moonshots around that are projects around the intersection of science and engineering to take those ideas to deeper scene understanding, to how do we develop as kids, as we're born as babies, and then we develop and learn to be helpful agents. Those are the kind of projects that scientists are now working on at MIT in combination with engineers. So it's take those sort of core ideas, science plus engineering, but apply them to the next intelligence problems. Again, to the goal of understanding human intelligence beyond just the early vision part, but also with the goal of trying to take the applications from that, because you're building an engineering understanding. As you have that understanding, you can deploy it for the betterment of the world.
So in regards to this intelligence project that you started to talk about, could you expand upon the moonshot projects? I'm assuming that that's under IQ.
Yes, so many of you may have heard about the MIT Intelligence Quest. So it's essentially built around that idea, is that part of what the Intelligence Quest is trying to do is there's two components. One is called the bridge, which is the goal is to take current AI techniques, which is mostly deep learning, reinforcement learning, and apply those to other areas of science, technology. You can apply it to chemistry, biology, anthropology, all fields, not only within MIT, but outside the world. So there's lots of things going on in that space, as many of these people in the room are probably driving themselves. And so that's what the bridge is about. Now the core is about, and that's where we're most involved, the core is about, deep learning alone is not the answer. Sort of early vision is not enough to explain human intelligence. So we need to understand the next level of intelligence algorithms, as I was saying, that would replenish the well of those algorithms, again, to then be redeployed in other ways through the bridge. So the core is really about the intersection of science and engineering that I was talking about, again, with the goal of replenishing the well of those algorithms beyond what we have today.
And what do you find is the most exciting work that's happening that you can discuss in greater detail for us?
Well, there's lots of lines of exciting work. I mean, again, there's the natural expansion is to go from beyond just vision to multimodal integration, to, again, deeper scene understanding, which starts to involve things like intuitive physics, not just knowing what's out there, but how things are sitting on tables likely to fall, that there are agents in the world. These are all the beginnings of sort of deeper scene understanding that beyond current vision systems. And then there are sort of even larger goals. I mentioned development, right? So you can look at, my colleague Josh Tenenbaum has a great, likes to show a great video of an 18-month-old just without language recognizing that you can tell needs help and just becoming a helpful agent. And so kids are born with innate abilities, and they learn even over 18 months to be able to be intelligent agents, even pre-linguistic. So that they have a moonshot project, both Josh along with some engineers and also brain and cognitive scientists, to try to build systems that are born like babies and learn like children. But those are just two examples of moonshots, and what we're really excited about is, again, there's lots of things to do in this space, the intersection between science and engineering, and I just named two of the examples there. And this is still being formulated by the faculty at MIT and beyond.
Wonderful. Well, thank you so much. Let me see if we have some time to take audience questions. We do? Wonderful. Anyone in the audience have any questions for Jim?
On your search, when you look into this development, how much of the intelligence of, for example, this baby is determined by himself or itself, and how much comes from the parents?
Oh, these are great questions. So first of all, this is not my exact area of research.
Question, please.
Oh, sorry. Would you like to? Or, so I think the question was how much. When you try to, say, study developing kids, and if you were trying to build algorithms that worked like developing kids, there's this question of how much is built in and how much is provided by the environment, and you asked in particular how much is provided by the parents. And these are kind of long-standing questions, just like object recognition was a long-standing question in cognitive science. These are open questions in cognitive science. There are data around those things, but we don't actually have full working algorithms. We have ideas of algorithms, and the goal, again, is to implement those ideas, compare them with data, collect more data that would inform on exactly those kinds of questions. All of these things are more complicated, as you might suspect, than just, oh, parents don't matter, birth doesn't matter. All of this matters, and so you have to actually engage with a full algorithm, not try to get stuck in, is it, it's all born in, or is it all learned, or what's provided by the parents. And that then exposes how you might intervene, how parents might intervene, as we have a better understanding of this, how they should change, how they work with their kids. I mean, these are the long-term goals of having, if you have algorithms, what you would do with those things to help us know how we should be training our kids. But this is really the beginning. I mean, this is why it's called a quest. We don't know the answers to that kind of question. I could point to studies, or my colleagues could, but again, we don't know it in an engineering sense of the term, which is what we're seeking. So I know that may be dissatisfying, but that's where we are. Yeah.
I had a question about memory and how cognitive processes translates into short and long-term memory. And is that also part of your study, the basis for memory?
So just to repeat that question, the question is regards to long and short-term memories and how your research informs that area.
Right. So you may know, again, the history of deep networks. First, they started out with you transform images, and you're going to do sort of static processing. And the more recent trends is you start to add in units that act as little memory holders, so little recurrent networks that essentially hold states over time, which you could call the beginnings of memory. And cognitive scientists for a long time have said, yes, we have forms of memory, have behavioral measurements of memory, but we haven't really known how to implement that again in algorithms. And I think these extensions of these algorithms, which are now recurrent, have essentially neural network-like buffers that you could call forms of memory, some shorter, some longer. Searching the space of those algorithms and finding the ones that explain the kind of memory-related behavior is what we're really after. So to take your question from an intuition about memory to an actual algorithm again is really the goal. So I know, again, I'm not really answering, I'm telling you what we need to do as a field.
And let me see if there's anyone in the back that hasn't had a chance to ask a question.
To what extent are we limited by silicon versus using biological substrate to get real advances? Because we just use 20 watts, like you say. Do you think are we actually at a barrier, or can we just keep using silicon?
So the question is there material barriers, one being silicon, for this type of work?
At some point, of course, we think that's going to be true. Right now, even running a GPU, it's like 200 watts, right? So, and that's just to emulate some parts of aspects of vision. So, the need to do that will probably come from, again, folks in this room, and our lab has gotten more interested in this too, of how can you implement this thing at lower power, right? I mean, ultimately, you could simulate anything on a well, not anything, but you can simulate on a machine, but it's not power efficient, and so efficiencies will sort of drive that. And it's not something that is the,
So independent of power, do you think we've got everything in silicon,
Well, so this is you're getting into almost philosophical questions. Some people would believe that you can't actually have kind of human-like intelligence without putting it in the exact same way, where I'm not one of those people, because I think intelligence is just a functional reflection of a bunch of interacting parts. And but again, I'm not saying our entire field buys that point of view. It's just the working definition that we work under, and at some point power will force us to say, and it already is forcing us, as you're building these algorithms and searching them, you know, folks again like Google are like, let's go from GPUs to TPUs, and that sort of allows you to test more things. So those developments, I think that's what's exciting, because engineering's starting to say maybe we should build things in these neural-like architectures, and as long as they don't go too crazy to say, let's build it down to like channels and try to, again, put in a lot of detail, which again is risky because we don't know what details are important. These things are going to allow us to answer those questions, which are really long-standing, right? I mean, that question will probably be answered maybe probably long after I'm gone, but sort of over the decades as we keep pushing these things. But I told you my bias on that, yeah.
One more question, our last question.
A lot of human intelligence is mimetic. Behavioral responses are mimetic. Our growth is mimetic. Intuition is mimetic. How do you, how do you burn an instrument which can do mimetic responses? Mimetic is, as in, if you nod your head, I do it because you agree, and so I force myself to agree, and then we eventually agree. Then I don't agree, then you don't agree.
I see. So you're saying responses are mimetic, meaning...
A lot of organisms grow faster because they're mimetic. They do something without thinking, and eventually they learn. That's how babies learn. That's in response to his question. So it's what the parents do. It's mimetic. Like, I do it because you do, because I trust you. And then eventually I teach you what to do, and then I do what you do.
Well, I think, again, if my colleagues that work on development were here, they would probably agree with you and say, well, these are the kind of things that we need to make sure those algorithms capture. Again, I think we have important intuitions, as you say, but actually...
Yeah, so this biology of leadership, that is mimetic. Great leaders are very good in mimetic response.
Now you're actually raising kind of theory of mind that a lot of what human communication is about is trying to influence other minds and sort of having agents that I know that you're an agent and my goal is to try to influence. You have a model of my mind, I have a model of your mind. That's called theory of mind. And again, many of my colleagues at MIT work on exactly that, and it's neural instantiation. And there's certain algorithmic implementations of that, but they're really just beginning. I mean, again, you're touching on sort of the things that need to be added as these algorithms are developed.
So the goal is to teach machines empathy. That's what they're lacking. That comes from mimetic. Empathy should be mimetic.
That would be one of many goals. I would agree. Yes, yeah, and that is one of the moonshots people talk about, is around empathy and emotion. Yeah.
Well, wonderful. Well, thank you so much, Jim. I think we are out of time here.
Okay. Thank you.
Welcome, Surya. It's so nice to have you.
Thank you. Yeah, great to be here.
Well, to get started, just as a quick introduction, I think at this stage of the conversation, all of our names get extremely difficult. So Stewart Ganguly, you are assistant professor at Stanford, and as I was doing my research, I realized it wasn't just in one discipline, but in multiple disciplines. So neuroscience, electrical engineering, computer science. Did I miss anything?
Physics.
And physics. And physics is the main one, the physics. Beyond your day job, which sounds like it's going to keep you enormously busy, you're also a visiting scholar at Google. Is that correct?
Yep.
Wonderful. Well, it's really nice to have you.
And I should also say I'm a scientific advisor to Manifold.ai, which is a super awesome, just to give them a plug, it's a super awesome data science company filled with people close to my heart who have been trained in physics and do awesome work on data science. If you need to hire them, go for it. All right, thanks.
Well, in vein of that,
you weren't expecting that, right?
No, I wasn't expecting that. But that's perfect opening for me. So in vein of that, sort of moving towards your love of physics, can you kind of talk us through, the applications that you're looking at within the AI space?
Yeah, I like to think that what we kind of work on is sort of this intertwined quest to both understand biological intelligence and create artificial intelligence. And we're actually a theory lab. Like, we'd like to have a scientific understanding of how both humans and animals and machines, how they all learn and work, right? And this, you kind of touched upon this, is there a divergence or convergence between machine learning and neuroscience and so on? I think there's actually an incredible convergence because for the first time in machine learning, we have nonlinear distributed circuits that actually do really interesting things that no other artificial system can, like machine vision, speech recognition, language translation. And we have humans that do the same thing. So we can compare the two and understand the similarities and differences. We can turn machine learning onto the brain to understand data from the brain. We can use inspiration from how artificial circuits work in machine learning to understand what the brain might be doing. So we kind of work at the nexus of all of these fields. And we use ideas from applied mathematics and physics and computer science to really have a scientific or quantitative understanding of what's going on. Yeah.
Wonderful. So could you kind of expand? I know that some of the work that your lab has done has been very similar to what our last speaker talked about, which was sensory images and neural circuits. And that's core to the work that my team is looking at in terms of diabetic retinopathy and imaging. Can you kind of expand on that space?
Yeah, I can give you sort of, for example, two applications. Like one is, for example, the retina, right? It turns out your retina is an incredibly sophisticated predictive machine that is doing a lot of short time scale predictions for you, right? And we still don't understand how the retina processes natural images, right? And nobody has actually come up with a good model of how the retina processes natural images. To our knowledge, we have the state-of-the-art model that does that at the moment. And we trained a deep neural network to mimic the retinal response to natural images. Then we looked inside that model, and the interior of that model behaved just like the interior of the retina. And then we threw like 50 years of physiological experiments that people have done on the retina, and our model got every single one of those experiments right in the sense that it behaved the same way as in the retina. Now, what can you do with this? So there's a big push to create retinal prosthetics, right? So there are lots of situations where you have degeneration of your photoreceptors, so your retina cannot absorb photons, but downstream, the electrical circuitry is intact. So maybe we can circumvent the light channel and directly stimulate the retina. But then what electrical patterns do you use to stimulate the retina, right? You first have to understand it. You have to understand how how light patterns are transduced into electrical patterns to basically learn the language of the retina, and that's what our model does. And then you can use that understanding of the language of the retina to then talk to the retina, stimulate it in the right way, and create much more efficient retinal prosthetics. So that's one example. And then just another example at a completely different scale. We had a collaboration with the Khan Academy a while ago where Sal Khan actually gave us a data set of about 50,000 students just solving math problems, right? So we'd like to understand the cognitive processes that lead to learning mathematics, right? So what we did is we modeled the brains of these 50,000 students using a recurrent neural network that just took in the history of math questions and answers the students gave, and it would predict how well it would do on every single math problem that you could give that student. And we actually got state-of-the-art predictions about how the students would behave. Now again, what application would that be? It basically has to do with control or teaching, right? So a little analogy that we sometimes think about as teachers in control theory is that teaching is fundamentally a control problem, right? The teacher's the controller, the student needs to be controlled, and the teacher has to send signals to the student to reconfigure the internal brains of the student so that you can transfer knowledge, right? So now that we have a very good model of the student using this recurrent neural network, we can interrogate that model and ask, what is the next best question to ask that student in order to increase their skill set? And actually, we could read off the skills of the student by looking at the inside of the neural network, because the neural network was a model of the student, and so we could figure out what the student knew. And so basically, we could tailor questions to each student based on the skills that they learned that our neural network inferred that they learned. So there's this beautiful interplay between biophysics and deep learning and the retina, all the way up to cognitive science and mathematics and, again, deep learning. So that's kind of an illustration of some of the things we worked on.
I'm going to take a side tour because that was so fascinating, but it sounds like there's so many applications to how we can really transform the way in which we get educated, both in our educational system and self-education. Can you, beyond research, is there applications of that's being used in real world today, either in some of the companies that you mentioned early on or other ways?
There's actually, so in the context of education, there's actually a lot of education startups that are trying to use theories of reinforcement learning where you give agents rewards and they use those rewards to improve their skills and so on. And so there's well-defined theories of how students and agents might learn depending on sequences of rewards and questions and answers that they're given. And they're trying to optimize the learning process in models and then applying that optimized learning process to students themselves to see if it works on the students as well. So there's actually a bunch of ed tech startups in that a colleague of mine at Stanford, Emma Brunskill, actually spends most of her time working on that. So that's something to look out for. I mean, we all talk about income inequality and so on, and I think this is a place where machine learning can really have a great impact on society in a way that ameliorates some of the inequalities that machine learning itself introduces into society. So it's great that there are people working on that.
Wonderful. Well, shifting gears slightly, as you look in the future in terms of what we have today in AI, what assumptions do you believe may be overturned in the future that won't last as research continues?
Yeah, so in the field of machine learning, there's sort of this cowboy attitude that you can start with a tabula rasa, a random neural network, and just train it and it will do all sorts of good things. But in reality, if you look into evolution, the human brain is a product of 4 billion years of evolution. And only recently did we really become human, right? And language only developed 50,000 years ago. So there's been a lot of structure built into the brain, into the human brain specifically. The human brain is not a tabula rasa. And so understanding basically the interplay between nature and nurture and how they work together to create a sophisticated learning machine that can learn very quickly from a limited number of examples, I think that's one of the pieces of conventional wisdom that need to be overturned, the current way that machine learning is done. And I'll tell you, there's a huge slice of the pie to be won there, because if you probably heard of AlphaGo, right? The algorithm that could beat the world's best chess player. If you look at how many games AlphaGo practiced, it turns out to be equivalent to 20,000 games a day, every day for 30 years, right? The world's best Go player never played anywhere close to that many games, yet it gave AlphaGo a good run for its money, right? So this has direct implications for business, because in many business applications, you just can't get that much data. So our ability to train in niche markets on small amounts of data would be a huge business win. And so it's all tied together, like tying together how the human brain works, translating that into machine learning principles, using it to learn from limited data, and then ultimately making money. It's not that easy, but yeah.
Well, with that, I think we have a couple of minutes for Q&A from the audience. Any questions?
My question really is about going back to the biology, right? Because we emphasize a lot on human intelligence, and then we're measuring that in so many different ways. Are we truly intelligent in the way we are defining? Because if we are going to be providing the input and it's our behavior that is being modeled collectively with over large sets of data, is it still the best gauge of intelligence? Even if it's collective, it doesn't matter.
Yeah,
we're really basing everything on patterns, but there's past.
Yeah.
Can we, from scratch, design something that has no past?
Yeah, so I think intelligence is a little bit of a nebulous term, right? It's just one word that means different things to different people. There's certainly capabilities that humans and animals have that far outstrip the capabilities of artificial systems. I actually work not only in humans, I work on flies, I work on mice, on monkeys, all that kind of stuff through collaborations. Like, if you look at the fly, it's like an incredible fighter jet. Like, it turns on a dime and creates torques that would be unimaginable if you scaled it up to the scale of a human fighter jet, right? So I don't think we should think of it as just one monolithic thing, intelligence. We could think about the capabilities that animals and humans are really good at, the capabilities the machines are good at, and ultimately we should augment humans, and also we should put humans and machines in the loop so that the strengths of the other can help the weaknesses of the other, right? So it's not going to be one monolithic kind of thing that happens. Yeah.
As you talked about the AlphaGo 20,000 games, 30 years, you talked about the S-Tech, the reinforcement learning. So I'm just wondering, in the S-Tech case, the reinforcement, for instance, students will have very limited experience with this learning platform. And what's your thinking on basically how do we with the lack of data, and how to give the best learning experience?
Yeah, so there it all boils down to modeling. Oh, sorry. So the question is, how can, if I understand it correctly, the question is how can we give students the best learning experience with limited data, right? So there, I think you really need to bring in the neuroscience and cognitive science to inform our models of the students. And as in all control theory problems, the better model you have of the thing that you're trying to control, the better you can control it. And that translates into teaching students better. So there's a whole army of researchers working on better cognitive models of student learning in different domains. We contributed a little bit with our model with the Khan Academy. So that's the way we can do it. It's not just going to be simple reinforcement learning with no model whatsoever, right? In fact, many machine learning, I've spoken to people like Jeff Hinton and Jan LeCun. They all think that that's going to be a disaster if you just try to do reinforcement learning from scratch with no model of what you're trying to do. So model-free reinforcement learning will be a disaster. You need a model of the world.
Yes,
Yeah.
over there.
Your classes must be fascinating. And as a math major, I have to ask, what did you find from what was most effective in terms of learning models from the Khan Academy math?
Oh, it's actually super cool. Like, there were like 60 or so different problem types spanning all the problems that students do in elementary school, like fractions, arithmetic, so on and so forth. And what we could do is we could predict, like if you were good at one set, what else would you be good at in the future? So then we could draw a graph. Like, knowing fractions will help you do something else, or knowing division will help you do fractions and so on. And we literally extracted this graph from the dynamics of the neural network that was trained on students. So we're looking into the minds of 53,000 students through the lens of this neural network. And when we extracted this graph, it looked like the prerequisite structure that educators came up with when they were designing curricula for mathematics. But there were some noticeable differences, right? So it's kind of like the educators got a lot right. But if you take a hard-nosed, data-driven approach to education, you could maybe even do better, right? So we were able to extract, for example, the prerequisite structure from the network.
How is the rate of our understanding of the brain going? Are there new tools being developed? Is that yielding research?
Oh yeah, it's incredible. So the question is, how has the rate of our understanding of the brain been improving? So I'm like this lazy guy that doesn't do experiments, right? I just do math, I do simulations, and that's it. Yet I'm still allowed to work on the brain. Why is that? It's because experimentalists who are actually collecting data from the brain can collect these ridiculous data sets with thousands or tens of thousands of neurons recorded simultaneously while a mouse is navigating a virtual reality task. And they can even write into the brain. So this thing called optogenetics, where you can shine light into the brain and make neurons fire. So you have this dream experiment where you can record like thousands of neurons, stimulate neurons, however which way you want. And now they need theorists to help them, analyze the data, design experiments, driven by theory and so on. And so basically, there's been these experimental revolutions in neuroscience that basically make neuroscience sort of a cutting-edge field that really needs input from physics, applied math, machine learning, computer science, and so on. It used to be the case, maybe 20 years ago, that biology is where people who are scared of math ran to. But actually, we need many more people who are really good at math and technical disciplines in biology now. It should be the place where physicists escape to, which is what I did. I did my PhD in string theory. I don't know if that, so I was in a completely different world when I did my PhD in string theory. And I took my first neuroscience class at the end of my PhD, and I just fell in love with the subject. And it was actually super easy to make a transition because they needed technical people.
Another plug for careers and jobs for those people out here, the early stage companies. I think we have time for one more question.
So question of, a lot of talks on how to model mind and so on and so forth. So is there any, or your thoughts on where proper consciousness is, and is there a way to simulate that? And if so, there's some models in the past about qualia and all these other things, taking biological, physical models and so on. So just wanted to get your thoughts on, where we are, what's the cutting edge?
Yeah.
And also, is there runner or ex machina scenario imminent anytime soon.
So the question is around consciousness, and are there any models in consciousness?
So you use the C word, huh? Okay. So actually, that's becoming a scientific discipline. That's left like basically the useless halls of philosophy, right? You can actually turn that into a scientific question. For example, you can record from an animal or human's brain, and you can find neural activity patterns that are necessary and sufficient for conscious perception. So for example, you can show very high frequency stimuli to a human or a primate. They won't be sensitive to it, but activity in your visual cortex will be entrained to that high frequency stimulus. So that tells you activity in your visual cortex isn't sufficient for consciousness. What seems to be the case from these studies is that you have this wave going from your visual cortex to your frontal cortex, which makes decisions, and then it comes back. And once you have this kind of traveling wave, you often get conscious perception. So people are trying to sort that out and make that scientific. It's difficult, though, because it's hard to get conscious reports from animals. It can be done through their subsequent behavior, but yeah.
Do we have time for one more? We have time for one more.
Yeah. How do you measure it? What are the apparatus to measure those thousands of neurons?
Oh, yeah, so there's many, many methods. So there's these multi-electrode arrays where you take many, many electrodes that can detect voltage deflections that are created by neurons when they fire their action potentials. And there you can record hundreds of thousands of neurons now. There's also calcium imaging, where you genetically rewire the brain so that whenever neuron fires, calcium rushes in. That creates this new molecule to fluoresce, and that emits light, and you just collect the light. So you can literally turn electrical signals into light and watch it through a light microscope. That's a really hot, and you can get about 4,000 neurons right now and hopefully 10,000 or so in the future. So it changes the ball game in our ability to probe the brain. And that also allows you to write into the brain as well. Okay, thanks.
Well, wonderful. Well, thank you so much.
Yeah, thanks.
It was a pleasure.
Sure.
Welcome, Bean. How are you? It's good to see you.
Thanks for having me.
Of course. Another fellow colleague at Google Brain.
Yeah. Although we just met today.
Yeah, that's true. It's a big team. Well, Bean, I think we're going to start with your focus work, in which we've already discussed that I'm going to butcher this in terms of the pronunciation, but interpretable machine learning. This has been your focus at Google Brain.
That's correct. In fact, it has been the focus of my entire research career. Like, I remember first time I started my PhD, and I saw this powerful tool, machine learning, being used or about to being used everywhere. And I asked people, so how does this work? How is doctors going to understand what this thing does to make high-stake decisions? And people told me, well, it's pretty good. You don't have to worry about that. And I was like, what do you mean you don't have to worry about it? And then I came to realization that not many people in machine learning had thought about at that point to work on this topic. Then I was like, well, this is a really important topic. I will start working on it. And I remember at the beginning of my research career, people were asking me, what do you work on? I work on interpretability. And they were like, okay. And then they would turn back and walk away. Why do you worry about it? You have high-performance network.
Well, maybe you can help the audience understand, what interpretability is to start with, and then what is the role of it within the discipline of machine learning?
Yeah, absolutely. So interpretable machine learning is about, unlike the how difficult it is to pronounce it, it is about how to make machine learning more understandable by humans. And this matters because machine learning is a powerful tool being used everywhere, and we want to make use of it responsibly. And what do I mean by that is to ensure that this tool reflects our values, such as fairness, and also appropriately reflects domain expert knowledge, like doctors' expertise, whenever appropriate. So there are 3 different ways to apply interpretability or improve interpretability in your model. Often people just think about building decision tree or logistic regression. But that's not only one way to improve interpretability. You can even do something before building any models. So data visualization, data exploratory data analysis all falls into interpretable machine learning. Now the second part, if you have power to change your model, then you can build a machine learning model that is inherently interpretable. What do I mean is, when you build an objective function to optimize for accuracy, false positive rate, or whatever that you care, you can also make it to optimize to learn explanation. And that's a couple of work that I did in my dissertation. For instance, you can use examples to mirror how humans make decisions. Recognition prime decision making has been well known of a way how experts make decisions. They, instead of looking at rule-based or feature-based, humans tend to look at examples. So firefighters, when they go run into this new incident, what they do is think about all the past fire incidents that they had participated. They look at what was the closest match. They remember what they did then and apply or reapply the solution if it worked, or modify a solution if it didn't work. So those are some ways that you can build inherently interpretable machine learning model. Third way of improving interpretability is if you have already a model that is trained and given to you. So this is often the case if you work in industry. You have a model that 10 years of engineering time gone into, you had highly optimized it, it gained trust in the company. You can't really change it. Then what do? There are some smart ways you can still probe at this complex machine by either using sensitivity tests or some of my new work using directional derivative, where you can test network using high-level concepts, even if that concept didn't really exist at the training time. So there are lots of ways to do it.
And help us, or describe to us how you can improve these interpretable models.
Yeah, so a couple of ways that I already described. But I'll talk a little bit more about my new work. So one of my new work is called Testing with Concept Activation Vector. It's just a fancy name for actually really simple idea. So neural network, well actually, how many people really familiar with neural network? How many people know like activation, high dimensional activation inside a neural network? It makes sense. Okay, so neural network is a bunch of functions stacked on the top of each other. And when you look at the internals of this neural network, it's super, super high dimension, 100,000 parameters. To humans, even if you have all the numbers available to you, it doesn't really make sense. However, there are some ways you can learn a direction in this high dimensional space that means something to us. So for instance, if you have a concept of gender, you build a network, you wonder whether this is biased, you want to make sure that your fairness value is aligned, then you can build a simple linear classifier in this high dimensional space to separate what is female and what is male if you consider gender as binary. And this vector that is orthogonal to this classifier turns out that well represents the semantics of gender. And this is not new. This has been discovered many times from the original work from Word2Vec and many others. Now you have this vector. What can you do with it? You can simply take derivative of the logit layer, which is the probability of whatever class, let's say doctor, with respect to this vector. And what that does is testing the sensitivity of this concept for this doctor. What it intuitively means is if I move a little bit along this vector direction, how much would my doctorness or probability of doctor change? If it changes a lot, it's an important concept. If it doesn't, it's not an important concept. So this is one of many really simple ways where we can help humans to gain insights, especially even if they don't have knowledge, the in-depth knowledge in machine learning.
And when would you not include it in your machine learning models or processes?
Yeah, so when do we not need interpretability? Yeah, it's an excellent question. So There are a couple of misunderstandings about interpretability. I am very passionate about interpretability. I've been working on this my whole research career. But there are definitely cases that you don't need to understand exactly how models or systems work. In fact, if you have flown in a plane in last month or so, you used one, and you probably didn't understand. Actually, there's probably non-significant portion of people who understand exactly how plane flies. In fact, there's probably people with pilot license in this room. But unless you do, you don't really understand how planes fly, right? Do we understand how planes don't crash into each other every single time? I don't.
No, I don't either.
Right? There's a collision avoidance system, which is an automatic system that when the two planes happen to unfortunately coming to head-to-head, then there's an automatic system to tell one plane to go up and the other plane to go down. Simple system. I don't understand it. But there's a huge amount of empirical evidence and trust engineering effort over many, many years that's built into it that we don't worry about it. And what that boils down to is when you have a system that is well tested and trusted, you may not need to understand every single thing about it. Another case when you don't need interpretability is when you can specify exactly what you're optimizing for in math. So for instance, let's say your only goal is to maximize a gain in investing stock market. I don't know anything about it, but let's say that you do, and that's the only thing you care. You don't care about other maybe societal impact of your trading. Then you can exactly write down the equation that you can optimize. Convex, great, just optimize, get the closed form solution. And what that means is if you have a problem that doesn't have fundamental underspecification, then you're all set. You may not need interpretability. You know exactly optimization that the goal function that you have for, go for it. But I challenge you to think about a case. Well, there aren't that many cases where you know everything about the problem. For instance, think about autonomous car. Can someone tell us what does it mean to build a safe car? Can we build a unit test that once a car passes all these tests, then this car is safe? We have the trolley problem. Even humans have this moral question about what to do in particular situation. So lots of questions that we encounter in life, in the world, in tech world, and outside of the tech world is underspecified problem, in which case we do need interpretability.
And what is currently lacking in the efforts of interpretability? Sorry, I have struggled. Yeah.
Yeah, so one of the, I've been organizing workshops at major conferences, ICML and NIPS on interpretability. And every time I do, I encourage all the psychologists, cognitive scientists, human-computer interaction folks, visualization, all these folks to join and help us understand better how human can better process information and fundamental understanding behind how humans work and things that humans don't do very well. So for instance, I have one study last 2 years ago about selecting examples that are both not only the majority of your sample, so think about data distribution like this mountain and there's a small mountain here, consider this as your majority of samples and consider this as your minority. Now when humans are given some samples from majority, they're happy to overfit your idea. This is idea of overgeneralization. And in fact, we are sort of designed to do it. And there are lots of studies that show humans are designed to overgeneralize for survival or to find a better partner. So we need an algorithm that can help us not to make the same mistake by selecting minorities, also sample from minority data distributions so that you can build a better, rich mental model of this complex data distribution. And that's one of many examples. I saw in many cases confirmation bias playing a role. If I give you an explanation, for example, in neural network, I give you a saliency map, which is highlighted pixels. It highlights important pixels in an image if you're classifying an image. And I showed that to a human, and when human looks at it, they immediately picks up the signals that agrees with what they already think, that agrees with their thoughts. And we see this in real life all the time in political environment, for instance. And these sort of fundamental understandings about humans has to come together, and that is lacking right now in effort to bringing these disciplines together. Surya, both Jim and both talked about how bringing these together and bridging the gap, make them talk to each other, work together, these are so important. Same story here, bringing them together, collaborate, develop a common language so that we can communicate and build a ground, a framework so that we can evaluate and iterate is important.
So with that, it sounds like there needs to be a fundamental language amongst the interdisciplinary researchers.
Yeah.
But do you also require that the humans and AIs need to collaborate?
Oh, absolutely. I think this is better put this way. So humans and AI is one way to think about it, but let's think about it this way, right? Let's say you're starting a startup, and you have a great technical skill, you love to code, but you just happen to be a person who hates to pay bills. You hate organizing things, or you hate dealing with the legal terms, understanding the words. And let's say that I have a friend whose name is Z, and she's amazing in organizing things, loves making order in the process, building up the more efficient and effective process. Would you want to work with Z? Right? So that you can do stuff that you love more and less of the stuff that you don't like, right? And it's the same story in human-machine collaboration. There are strengths that Surya pointed out, alluded to this earlier too, that machines have different strengths than humans have. Machines very fast at calculation, memorize every single thing, learn patterns. The humans are typically not good at reading. So would you want to work with this different organism that is good at something that you're not good at? Absolutely.
Well, wonderful. Well, thank you. I think we have a couple of minutes for Q&A here. Any questions from the audience?
Is the work on interpretability leading to some insights on why neural networks are working so well and why so recently?
I think the answer to that question is yes and no. There are some early insights that show, I believe this was work in early 2010 by DConvNet, work by, I think, Ziller et al. They developed a method to visualize the internals of each node in the neural network, from which they found that some nodes are just gradients are not flowing. And for those who don't understand, don't really know what I meant, it's just a way to say that there are this high dimensional activation layer that I talked about. Some of these nodes are not doing anything, and that means the gradients are not flowing, not doing anything. And so they discovered this part of the network that was basically dead, and they got rid of it, and they were able to build a better model. So that's like one of the first efforts to understand, by understanding it better, improving the model. There are other models that, more recently work from Stanford at Percy and Peng Wei. They worked on ideas to find out mislabeled examples in your training data set by using the influential function and by taking, scoring each data point to blame. And the higher blame it is, you find what was the most contributor for this misclassification. In my work, depending on what you mean by improving, I care about fairness in your network. So most recent work, I took Inception v3 and GoogleNet, which is one of the two most widely used image classification network, and discovered that these networks have huge gender and race bias encoded in it, as we probably can guess. If you pass Asian faces into this network, it thinks it's a ping pong ball. And the reason is, surprisingly, not many people know it's because we're good at ping pong. I'm from Korea, and I'm proud to say that we win a lot of gold medals in Olympics at table tennis. So that bias is encoded in this network. And if you mean by improving by aligning better with the values that we care, these are some of the ways to raise a flag and say, hey, we got to do something about this.
I was thinking about understanding why fundamentally neural networks are working at all.
Oh yeah, that's also so I think you're raising an important point. There are two different things about interpretability, two different natures. One is science. You have a complex model, why is it working? And second is end-task-based interpretability, which is understand just enough to do what humans, doctors do better. So you're asking the first case. There are lots of work done. Like for instance, now DeepMind just published last month or two about just killing some nodes in a network and see what that part of the neural network is doing. So it's all underway. Lots of work like rethinking generalization. Those great survey papers also serves that tool.
At the recent NIPS conference, there was a statement that AI is currently in an alchemy stage, to which Ian Lincoln replied that, oh, this is actually what engineering looks like. And since you're working on interpretability, where do you think currently deep learning is in the rest of smart systems AI?
Where is the deep learning in the axis of rigor? Is that the question?
You can interpret it.
Just the the question I think is, where is deep learning? Where is it? I think we're in a critical moment when the difference between, so let me rewind. So the interpretability question of having complex machine understandable by humans is long. It's an old study. Like expert systems is in 80s, before I was born, that people looked at this and taken this very seriously. There are lots of expert systems, lots of lessons that I need to learn, we need to learn from that system. Now, what's different? Why is it important now, this topic of interpretability, is due to two things, complexity and prevalence. It's everywhere, and it's more complex because we just happen to have more computing power to make it more complicated for ourselves. But we have a lot of them, and it's cheap, so it's everywhere. I challenge you to think about a day without using a tool that is machine assisted. Even if you're camping out in the wild, your camping gears might be optimized using machine learning. So you're embedded, this machine learning and AI is embedded in your life, and you have this unique opportunity to importantly understand the machine learning so that the societal impact of this powerful tool could be positive. So where is it? We're at the beginning of a very crucial moment where, in my biased opinion, interpretability is very important.
Why does this bias originate? Is it like you're talking about like fairness, and so is the bias originate from like the data is biased? There's like bad ratios. Like what's the origin for this bias?
Yeah. So the question is, where is the origin of the bias in the network? Lots of things. So data is obviously clearly one issue, and the model can be another issue. Your optimization function. So for instance, let's talk about the data first. If you have a data of doctor pictures and you just happen to have a lot of men in it, then clearly your model is going to be more accurate. It has more information, more variance that it has seen in the training data set to guess what this picture is. So of course it's going to do better. But that's not all. Sometimes, lots of fairness folks in the academia talk about and study what is the fair metric to encode for a network to optimize. Even if you have a skewed data set, if you have the right metric, you might be able to achieve some fairness. So for instance, you can explicitly hit the balance between false positive, the accuracy of subgroups, men and women, and you can explicitly optimize for that. So there are lots of spaces you can improve optimization and lots of places where you can cause bias.
I think this is our last one. Last one.
So just as we are witnessing with great technology, not only the great potential for mankind's improvement, but there's also great potential for mankind's destruction. Do you feel yourself responsible for taking the other kind? I know you were 6 years now.
Oh, you're a little quiet later on. Say it again.
Sorry, I didn't hear you.
Could you repeat? Excellent. I said I didn't hear you, and you're going to repeat the question. Last sentence.
With great technology,
Yeah, I heard that part.
There is great potential for mankind's improvement, but there's also great potential for mankind's evil. Do you now, within the Google complex, worry about such issues? And do you still have that scholarly mentality that we will keep pursuing this for the research?
Oh, that's a great question. Thanks for asking a question. At Google, we take this very, very seriously. And before I joined Google, I sort of maybe was in similar boat. Like, it's a big company, you know, sure, they care about this issue, but do they really? They really do. And one of the reasons that I am feel incredibly lucky to be part of Brain is because we are in this center of, while we are pursuing academic passion, we are highly motivated and incentivized to also make real world impact. We're in a position where we can do that. So I take quite serious responsibility for making the positive step for the humankind. In fact, you know, if I don't care about that issue, I'll be probably doing, you know, something else, I don't know, art or something. But I feel deeply responsible for this. And I think Google is part of the place where there are lots of people care from bottom of their heart, from top down. And there are real processes and actions and movements to actually make this happen.
I think, thank you so much, Bea. I can also echo in that sentiment.
Yeah.
Thank you. And we have one last guest for you and speaker. Hi, Ramesh. It's great to have you.
It is Zeenat.
So Ramesh, just to sort of get started here with a quick intro, you are an associate professor at the MIT Media Lab, and you focus on camera culture research. Is that correct?
Correct so far.
Hopefully I have nothing incorrect to say at this point. Well, we'll just jump right into it because I know that we have a limited time with you, and we have slides, I believe, of some of the topics that you're going to be discussing here.
Right.
But you know, from your perspective, what research is required to push AI to the next level?
Absolutely. So, you know, my group, Camera Culture at MIT, we really love pixels. And we think about how do we capture pixels in interesting ways, how do we manipulate them, and also what can we understand from them. So the whole spectrum from physics, computation, and inference. And to me, kind of the two main areas I'm really excited about in AI is how can we automate machine learning. And the second aspect I'm very excited about is how can we have a true fusion of machine learning and physics. Because right now we're talking about machine learning and sensing, whether it's visual and audio and so on. But how do we have a true fusion of machine learning and physics? And you know, when it comes to automating machine learning, you know, we have the traditional ways of thinking about programming. And if you think about in the computer vision image analysis domain, if you had to detect an edge or a corner, you know, you would write a very specific procedure to detect those features. And this was called feature engineering. And over the last 30 years, great progress was made in how we can take maybe a 3x3 pixel patch or a 5x5 pixel patch and look at, you know, clever projections like gradients and, you know, remove the orientation. And we did a very good job of feature engineering. And then with machine learning, we said drop feature engineering, and features will be automatically learned by the first few layers of a deep neural net or convolutional nets. So that's been great. We went from feature learning to feature search. But as far as the architectures are concerned, we are still doing architecture engineering. And I think Jim was talking about AlexNet, or whatever favorite your net is still kind of well crafted by you know, some smart people. And then what's happening now is we're actually able to find the architectures themselves by doing a search automatically. So in that sense, it's really kind of AI writing AI. And that's really exciting to me. And when we think about, once you get experienced in a field, often like to say that kind of knowledge comes from analysis, but wisdom comes from synthesis. And so we pride ourselves, Malcolm Gladwell, 10,000 hours to get to that expertise, that level of wisdom. And I think same is true for machine learning, which is so far we have been doing either osmosis or this engineering to get them going. And now machine learning algorithms are kind of the knowledge and knowledge analysis, knowledge representation aspect of it, because they're doing a lot of analysis. But over the last few years, the machine learning algorithm is also doing synthesis. And I think that's really the exciting, but also the kind of the creepy, dangerous area, that once machine learning algorithms, ML algorithms can also do synthesis, then they really start absorbing, they start representing wisdom. So that's a very exciting direction for all of us to see how much wisdom can be built in this automatic machine learning algorithms.
Maybe you could expand on that. So what would be the positive implications of the synthesis process? And you sort of already touched on it, that there is some danger or creepiness. What are the areas that your team is watching out for as you continue down this path?
Yeah. So, I think the previous speakers have talked about relationship between child development and training machine learning algorithms, that, writing a program in the future will be very much like teaching a child. So you don't need a programming background to raise a child. And the same way, hope so, although I think it's still very useful. Sometimes when I talk to my wife, I says, see, I'm telling you, in the reinforcement learning, if we keep not preventing, having this, if you're not careful about the candies, they think that's what the reward is supposed to be. And the reward function has to be modified, and she, of course, rolls her eyes. And actually, a lot of faculty members, a lot of my colleagues now who teach machine learning expect grad students to take classes in child development as well. So kind of taking that analogy forward, if we have to create these algorithms, then instead of just writing engineered code, now we can teach them at a high level. If we take that concept further, we get into the world of automated machine learning. And so our group was actually one of the first to put this concept together. And if you look at the left, it's kind of the teacher network, and then the student network. So far we have been thinking about the student network, which is a network that kind of learns either from the data or from the environment. And that has been going on pretty well, supervised or unsupervised learning. And now we're getting into a mode where we also have a teacher, and the teacher is actually using a reinforcement learning algorithm to decide what should we do, what modification should I do in this student's learning process so that the student can get better and better. And really thinking about the school of teachers and students, what our group has realized now is that actually the teacher can train not one student, but many students in parallel, which means that it can train many algorithms in parallel. Given the history of AlexNet and ResNet and so on, going in this, we thought that, there's going to be 1 in a million or 1 in a billion architecture that's going to be really great. That's going to be really awesome. And we had to come up with this really magical teacher algorithm that finds that 1 in a million, because the same way Alex, as a student in Toronto, probably spent a lot of time figuring out AlexNet, we need to come up with this really smart teacher algorithm. It turns out that's not true. It turns out there are many algorithms, many models, many networks that will do roughly the same. And that gives us some faith. It's just like if you're a teacher and you're teaching students, it's not like most of the students are going to fail and there's going to be this one student who's going to survive and have a successful career. Actually, most of the students do pretty well. And that's what we are noticing in machine learning world as well, that actually you can start with somewhat random initial guess for the student networks. But if you train them and if you nudge them and prune or add parameters or pick hyperparameters, but especially change the architectures, not just change the parameters, so change the topologies. It turns out we can train many student networks that do roughly equally well. So we don't have to worry about this needle in a haystack problem. So this is kind of interesting. So now we're getting into a world where we can actually write AI that builds AI, but most of the AI is reasonably good. And if you continue to take that process forward, now it's just not about creating a student network that's good at a particular task, but now it's about the next generation of research that my team and many others are doing is how can we create those networks that are really simple. So for example, they're highly pruned. So as you know, most of the networks have roughly 100 million or more, 100 megabyte or more of parameters, 100 million or more parameters. But many researchers are now realizing that it can go 20x or 30x simpler than that. Even with 5 million parameters, you can actually do 80 or 90% as good as others. This is kind of fascinating. So now we're talking about your Amazon Echoes and IoT devices and all those things where you could have extremely pruned networks that do actually pretty well. And we don't have to kind of craft them, handcraft them, but they can just learn on their own. And more importantly, the teacher can be remote, and the student algorithms you can send them with initial guess. They go to my house and have a strong Indian accent, and they go to somebody else's place, and there's a completely different environment, but they can just train on their own and get better and better with a remote teacher. So this kind of teacher-student model seems to be fantastic for creating automated machine learning.
Wonderful. And then just to kind of come back to the two things that you said excited you. One was automated machine learning.
Right.
The second was this interaction between physics and machine learning. And maybe you can expand on where in that area you're the most excited about.
Absolutely. So in our group, we love to build all kinds of sensors and cameras. And for example, how can we create new types of LiDARs and time-of-flight cameras? Some of you may know this work we did on a camera that can create videos that appear to be capturing light in motion, 1 trillion frames per second. And with that, we can create sensors that can even see around corners beyond line of sight. So this is the work we have been doing over the last 6 or 7 years. And after building this solution, what we realized is that we shouldn't be limiting ourselves to kind of human-level performance of these AI algorithms, but we can create superhuman. Now, many people are thinking about how to be superhuman from a computational point of view, but we want to be superhuman even in the physics point of view. So think about a superhero who has the ability to see around corners. And now we have these rudimentary sensors that have the superhuman abilities. What does it mean to do machine learning on that? And Guy Satat, who won the AI Rising Star Award, also a student in my group, has been working on problems like fog and how can we combine data-driven techniques and so on. So coming back to physics, we thought if you think about self-driving cars, we're adding hundreds of thousands of dollars of electronics and sensors and computing on this vehicle. But remember, at the end of the day, the vehicle only has two unknowns, the speed and direction. So just to compute these two variables, we're spending $100K of sensing hardware and a big computing rack sitting in the back. That just seems very counterintuitive. But if you look at insects or bees, they're able to zip through with microwatt or milliwatt of power, with a few grams of total body weight. So that seems kind of magical. So why can't we do this biomimicry to do that? And of course, it's not as straightforward because we have to think about these fast, tiny, and low-power solutions. And the way we are solving that is, kind of simulate very complex cameras. You wouldn't even call them cameras anymore because they just sample the light in unique ways, not just visible light, but multispectral light, time of flight, like I showed you how you can see around corners, and create sensors that are highly task-dependent but could run on microwatt of power.
Mm-hmm. Ramesh, thank you so much. I think we had prepared so much more to talk about, but we're almost at the end of our time here. So let me take one audience question before we wrap this up.
like you have this net deployed on your Echo, and it can like understand the Indian, and then you have this teacher, and it can be remote. But why does that have to have this remote training? Why does that have to be a teacher-student model? Like, what does the teacher-student model get you for doing like training remote? Like, what advantage does it get you for that?
Yeah, so the question is, why does your Echo have to talk back to a teacher network? Why can't it just continue to become better and better on its own? So that would be standard machine learning. You have an algorithm that just keeps getting better with more supervised and unsupervised procedures. That would be standard machine learning. We're talking about a teacher-student methodology where the teacher has a more complex network, has a much better understanding of which path. We're using Q learning, which is standard reinforcement learning method. And it has this amazing wisdom and insights in what is going to work, and it has a memory and so on. So we don't expect such a large network to run on an edge device. And that's why you might want to communicate back and forth. So if you want to preserve privacy, of course you won't talk back. But for improving the algorithm without sending data, you might be able to do that.
Wonderful. Well, thank you so much, Ramesh. And thank you to all of our speakers today for the wonderful afternoon.
Thank you.
It's a pleasure to have you.